Okay, good morning. Are there any questions on anything from homework or anything from chapter 5, sections 1 and 2? Should be able to do those. Does anybody have any questions?
I had a question about one of the, or actually a couple of the problems asked to at first find the probabilities and then figure out what the probability would be if the experiment size grew. So like it would go from 300 to 1,000.
Okay. I don't know what the question is, so do you have
I
a
don't know.
do you know what the question is?
Just in general, it was let me look for it. I think I have it written down.
Okay, or if you just have like the question number, like where what section, what number it was, we can track it down.
It was 5.1. I believe it was question 13.
5113. Okay, let's look at that one. So the numbers themselves are going to be a little bit different here than what you saw. Um, this is a sort of a dynamic homework platform where every student has slightly different questions, like some of the numbers vary a little bit. So yours might be a little bit different, but hopefully it's similar enough. Is it this one? Something about bulbs? A bag of 100 bulbs purchased from a
No, it
nursery?
was about student athletes in a high school.
Okay. Well, this one's number 13 in the assignment. Do you think it was number 13 in the section? Right? So as I mentioned before, this homework assignment has a total of 22 assigned, right? So that's like number 13 assigned in the section. But then if you look in the book, this is not question number 30 in the book in that section. So maybe it's question number 13 in the book that you were looking for. Or do you think it had nothing to do with the 13?
Okay, I had trouble understanding. For me, it was question 21. It was a median. I didn't understand. I
Median.
understood it
Wait,
when I
hang on 1 second. Median. This is
yeah,
in question number 21?
question 21.
Is it this one? A recent survey was found. Oh, okay. Well, that's
Yes,
one
that
of the
one.
drawbacks of starting in chapter 5. That some of the definitions from chapter 3 and chapter 2 are kind of finding them way over here. Okay, I'm sorry. So keep going. You're saying?
So I had trouble trying to understand the median.
Mm-hmm.
My note it splits it in half, but to
Mm-hmm.
me, I didn't understand it when it came to this because I was leading towards I was trying to half the 57 and then add 57 again to get to the median of it, but I knew that was incorrect.
So
I
they're not saying for you to find the median. They're saying the median is 57,300, right? So the median is exactly the middle number. So here we're talking about incomes of families, right? So if we lined up every family in the country, like maybe not physically line them up, but electronically, we created a database that just has a list of all 320 million Americans. Well, this is going by families, not by individuals, but same thing, families. So all families in America are listed in a database based on their annual income. Of course, many of them will be really, 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 really high, and some of them will be really, really low. But if we put them all in a giant list and we go to the person right in the middle, then that income will be the median, and the median is, in this case, we're being told is 57,300, right? So by definition of what the median is, it's the one right in the middle. So therefore, if one randomly selected family is picked, there is exactly half a chance that you'll pick them above the middle value and half a chance that you'll pick them below the middle value, right?
right,
That's
so I put point 0.5,
mm-hmm.
but that's
Where's
where I got
where's
the
family?
confusion. Where I'm just like, well, why did I get 57,300 if I got point 0.5? But the way you stated it, where you went down the list to zero and then half it at 53, at 50,300, then I understood it better.
um, okay, I good. I'm glad, and just to clarify, just to make sure anybody that's listening, if I listed down Let's go over here. I want to write something down. Let's go over here. Right, so I'm going to list down income values, right? Family number one. Why is this in thick? So family number one, just kind of listed by income. I'm sure a lot of them are zero, right? For whatever reason, their income is zero. If we look at all the, okay, so eventually we get some, oops, family number two, family number three. You know, there might be a family out there that just lists $1 as their annual income, right? And in fact, there's a lot of people that just list $1 as their income. So then, you know, keep going. Well, let's see, I didn't mean for that to be ... So ... the 300th family lists $1, and then ... and family number 1,378,928. Maybe they list $37,520 as their annual income. ... Family number 978,248, right? So this is family numbers, right? This is an income. This is family number 28 million, right? I don't know. They live in Iowa or something. This is family number 1,378,000. You know, they live in California. You know, whatever. And then we're listing down their incomes, right? And somewhere down the line, we're going to get to a point where they say about 57,300. Good. There might be more than one family that has that number, right? Family number 28,978,249 also listed $57,300 as their income for the year, right? And then, of course, we keep going down there, and near the very top, there's the uber wealthy, right? Some really, really rich family. Family number, well, let's see, there's about 320 million Americans, so let's say there's about 100 million families then in this country. Just ballparking, I don't know what the real answer is, but let's say family number 101,298,308. I'm not saying this is the last family if we listed them all down, but we're near the end here, right? There's probably close to that many families in the country. And then they would list their annual income, and these are ordered from whoever made the least amount, which was $0, to whoever made the most amount, which is like Jeff Bezos or somebody, right? So one of these uber billionaires. So what's their annual income? Well, they probably listed, and I'm just making up these numbers, but maybe in the neighborhood of 20 billion. Maybe that's what their income is for the year. I don't know. I'm just making up a number. So we go from the poorest families in the country that made $0, and then to the richest families in the country that made about $20 billion. And the median is going to be the one that's found right in the middle. By definition, that's what it means. The median is right in the middle. Now, it's not in the middle of the numbers. It's in the middle of the family numbers, right? So as we list down the families from family number 1, 2, 3, 4, 5, the one that's right in the middle is the median. The middle. That makes sense? We list them all down from whoever made the least to whoever made the most. The one right in the middle is the one that results in the median. So by definition, if we randomly choose one of these families, we randomly surveyed, we randomly send a letter or an email to a family in the country and ask them, what is your income? Well, we got half the families are over here, and the other half are over here. So there's a 50% chance that we will randomly select a family over here above the middle, and there's a 50% chance that we will randomly choose a family over here below the middle value, right? That's what the median is. That's different from the mean. And when we actually go back and look at chapter 3, we will see the distinction between the median and the mean. But as long as we're looking at the median by description, by definition, is the number that separates the bottom half from the top half. Okay? Good. So this question was not asking you to find a middle value. You don't divide 57,300 by 2. We're not asking you to find the mean or the median or anything like that. That question was really unfair at this point because it relied on you understanding what the median is. And I know that we didn't cover that yet. So that's why you're kind of unprepared for that question, but we will get to those definitions eventually in chapter 3.
Thank you.
Sure. Okay. Other questions? Ready to move on?
I have a question.
Yes, question?
It was 12, not 13.
Question 12. Okay. Question 12. This one, a survey of 200 randomly selected students determined that 60 play organized sports.
Yes, so it asked this, and then I believe it was like a multi-part question, and then afterwards it asked what would be the probability if it were 1,000 students rather than the 200, and it would ask for what's the exact.
Here, let's just go through it then. So part A says, what is the probability that a randomly selected high school student plays organized sports? Okay. A survey of 200 randomly selected high school students determined that 60 of those 200 play organized sports. Does that mean that there are only 200 students in the school? No. There's 200 people that were randomly selected in the survey. Who knows how many students are in the school? Maybe there's 300 students in the school. Maybe there's 2,000 students in the school. Maybe there's a huge high school. Maybe there's like 10,000 students. Who knows, right? But this is not all of them. But of the 200, 60 of them said, yes, I play an organized sport, right? So what we're leading to here is empirical probability. If we want to know how many students in this school play organized sports, one way to do it is to start asking people, right? And get yourself a survey going, right? And the experiment is just to ask, hey, do you play organized sports when you randomly stop somebody? And you keep track of the results, right? So by empirical probability rules, if we just divide these two and we get a result of 60 over 200, which is 30%, 30% of the people in my survey indicated that they play organized sports. Therefore, that's my very best guess as to what the true percentage is of the entire school. Good? So it's just a guess because there's not everybody. It's not a census, it's a survey. I haven't accounted for everybody. Maybe it turns out that the real answer might be a little bit off. Maybe I just randomly picked 200 people that happen to have oversampled the population of students that do play organized sports, right? Maybe I thought I was being random, but I just happened to get a little group of people that kind of travel in packs. Maybe it just so happens that a bunch of players and whatever in some sport just kind of walked by the person taking the survey. So now you get a wrong sense of how many people play organized sports. That might be the case. We don't know. Right, that's why we need it to be truly random to try and minimize those chances. But okay, so at the moment we go by the information we have. By the empirical rule, we believe that probability is going to be 60 over 200, and then when we round to the nearest thousandth, it's going to be 0.300, I believe. Well done. Now, part B says, choose the correct answer below. Now, the question is, part B, interpret this probability, right? So when I say 30%, there's a 30% chance that one randomly selected high school student from this particular high school, there's a 30% chance that that student plays organized sports. Another way to interpret that is that we believe that approximately 30% of the population of high school students play organized sports, right? Those two sentences are equivalent, right? Let me repeat that again. Saying that there's a 30% chance that one randomly selected high school student plays organized sports is the same thing as saying that we think about 30% of all the students at this school play organized sports. So now, in order to come up with a sentence that describes that, we can phrase it in different ways. So one way to phrase it is in terms of thousands. So if 1,000 high school students were sampled, it would be expected that about 300 of them play organized sports. Why 300? Because 300 is 30% of 1,000. Right? So if it turns out that there's 1,000 students in this school, I'm guessing about 300 of them play organized sports. Right? And I keep saying guess because this is empirical probability, so we're not totally confident, but as the sample size grows larger and larger and larger, so does our confidence in this probability also increase. Okay? So what was the other options? If 1,000 students were sampled, it would be expected about 300 of them play organized sports. The other option is if 1,000 high school students were sampled, it would be expected that exactly. Okay, so again, this word, the only difference between these two is about versus exactly, right? And as I just mentioned, we are not 100% confident that it's exactly 30%. We're fairly confident, right? Empirical probability makes us be fairly comfortable with this answer, but it's not the exact answer. The only way we can get the exact answer is if we surveyed every single student at this high school and got an exact answer. So that would be a census rather than a survey. Again, we're a little bit handicapped in this chapter because it does rely on some of the definitions that are in chapter 3, but I think we can get by, and we'll come back and revisit those definitions when we go back to chapter 3. Okay, so let's get that answer. Fantastic. Okay. Did this make sense? Any more questions on this one?
No, it's good now. Thank you.
You're welcome. All right, let's get back to it. So let's get rid of this. Let's get rid of this guy. Let's go back to this guy. And I want to erase all this. Okay, we're going to look at another scenario to help us distinguish between the empirical probability and the classical probability. Right? So empirical, remember, is experimental probability. When you want to know something, when you want to know the probability of something occurring, one way to do it is just to repeat it over and over and over and determine what's the likelihood that something will happen. Say I design a brand new airplane, a whole new design. I put the engine in a weird place, and I think maybe that's going to be really good. How do I know that this airplane will fail? What are the chances? What is the probability that this airplane will crash? Okay, well, one way to do it is just to fly it. Let's just create it and go out there and fly it thousands and thousands of times and count how many times it crashes. Right? Of course, that would not be that wouldn't be a very good way to do that. First of all, money. You'd have to build this plane, and then it crashes, and then you build it again, and then keep track of how often it crashes. That's not good. So you're going to waste a lot of money. You're going to be putting a lot of lives at risk. It's not a good way to do it, right? So what's left? Maybe a computer simulation. Right? I do a really well detailed computer animated interpretation of my design, and then we put it through a simulated real world environment where we get to decide the likelihood that it would crash. It's not going to be the actual answer because obviously it's just a computer model, so there's a possibility of flaws, but that's where we would begin. Okay, so we could create simulations in order to help us understand situations. So here's an example that we're going to look at here. Let's say that we have 4 babies born in a hospital, but, babies all look alike. So maybe the nurses kind of made a mistake and kind of swapped them around, and now they don't remember whose baby belongs to who. And then now it's time to go home, and the four mothers are, waiting for their babies to be handed to them so they can go home with their babies, and kind of fingers crossed that they actually get their correct baby. This is probably unlikely today, since we do quite a bit of technology to make sure that doesn't happen. Right, as soon as the baby's born, they put a little bracelet thing on there, and then like the computer can track all the movements of the baby throughout the hospital. But I can see this being a real issue before all those steps were put in place. So back in the 50s, 60s, or below, it probably happened from time to time, right? I mean, babies all look alike and whatever. So you accidentally misplace it somewhere in the nursery area, and it's possible that the wrong baby went to the wrong family, right? Okay, so what we want to do is explore that scenario. 4 babies are born to 4 mothers, and then it's time to go home. The nurses got it all mixed up, so they just kind of randomly assign babies to mothers. And we want to know probabilities. What's the probability that all 4 babies went to all 4 correct mothers? What's the probability that 3 of the 4 went to correct mothers? What's the probability that 2 out of the 4 got their correct baby? What's the probability that none of them got their correct baby? What's the probability that at least 2 of them got their correct baby, right? We want to answer all of those questions. So we have a couple of ways to do that. One of them is classical probability, and we'll explore that here in a little bit. But we also have empirical. So empirical means we create a model to simulate the situation. Good. So that's what this is. Let's go over here. Rossmann chance. You can just Google this. Rossmann chance random babies, and it'll take you to this. It's an applet online that just helps you simulate this condition. So what we have here is the hospital. We have 4 different houses identified by colors. So we have like a purple house, red house, green house, and a yellow house. And we're going to simulate one little thing here, right? A little stork comes, little babies come, and then based on that, you can tell who went where. So the little sun indicates sunshine. So this was the correct baby, went to the correct house. And these little storm things indicate that a mistake happened, right? So wrong house, baby went to the wrong house, baby went to the wrong house, baby went to the wrong house, okay? Now we're going to keep track of that. Since this is empirical probability, it's important to do it over and over and over and just keep track of what happens. So over here, we can see that right now, there was only 1 correct assignment. So the first time we did this, there was 1 correct selection, okay? Then we do it again. See how the red goes to red, purple goes to purple. So these 2 were wrong, these 2 were right. This time we had 2 correct ones, 2 correct results. Good. And then we do it again. Again, we had 2 correct results, and then we do it again. This time we had 1 correct result. See, let's go through until we get 1 of each. No, this one's going to be the case where we have 0 correct. All of them were wrong. That's why this little bar just went to a 1 there. So far we have 1 case where none of them were correct. 1 case where 2 of them were correct. 2 cases where 1 of them was correct. 2 cases where 2 of them were correct. Right? Okay, so speed up the thing. Let's see if we can get a 3 and a 4 in there. Here's another case where there was only 1 correct match. I'm going to go until we get a 3 and a 4. Nope, that's going to be 2 correct matches. Okay, 2 correct matches. Okay, so we're starting to get a sense of what typically happens when this mistake occurs. Looks like 2 is very common. 2 correct matches. 1 correct match, 2 correct matches. Those are very common. So far, we haven't seen 3 correct matches at all, and we haven't seen 4 correct matches at all. So maybe I'm starting to get a sense that maybe these are more rare, right? the 0 correct matches only happen once as well, so maybe those are also not very common. Okay. Also, this little table up here is keeping track of everything. Oh, and look, we finally hit a perfect pitch here. Everybody got their correct baby. Good. Okay, so this thing is keeping track of what's going on. 1, 5. Okay, so far I've done it 10 times. Number of trials, 10. So I've repeated this process 10 times, and so far I've gotten that out of the 10, only one time I had 0, only one time I had all 4, 4 times I had 2 correct babies, and 4 times I had 1 correct baby. So if I was going to stop right now and give my best guess as to what these probabilities are, they would be right here. 1 out of 10, 10%, 4 out of 10, or 40%, 4 out of 10, which is 40%, and 1 out of 10, which is 10%. Good. So this is my best guess. This is empirical probability, right? If somebody stopped me right now and said, what are the odds that exactly 2 babies go to the correct families and 2 babies go to the wrong families, my best guess, based on these 10 trials, would be 40%. I wouldn't be very confident in that answer because 10 is not that big of a number of trials, right? Empirical probability tells us that, well, the law of large numbers tells us that as we repeat the experiment, as we repeat the number of trials more and more and more, the more we repeat it, the more confident I am that these probabilities will approach the real ones. So instead of doing them one at a time, let's see, can I just hit a 10 there and then it'll automatically do 10 of them? Good. So then I hit 10, it automatically did 10 more. Notice that now I've jumped to 20 trials. After 20 trials, these are the results now. 5 were cases where 0 babies went to the correct household. So currently, I have a 25% chance, right? The empirical probability tells me that it's about 25% chance that 0 babies go to the correct houses. So far, out of the 20 trials, 3 of them were cases where all 4 went to their correct houses. So at the moment, I'm thinking it's about a 15% chance. Notice that there has never been a case where exactly 3 of the babies go to their correct house. So at the moment, I'm thinking the answer is 0. Good. Okay, so let's do it again. So now out of 30, out of 40, out of 50, let's do it up to 100. So here is after 100 computer simulated trials, now I'm getting that, oh look, 0 is actually the most common thing that happened. 0 cases. When there was only 10, I thought it was kind of rare. But now that I've done it 100 times, I see that it kind of comes up pretty often. So at the moment, after 100 trials, I'm thinking 37 out of 100 times we got cases where 0 babies went to their correct houses. So I'm thinking it's 37%. 32 out of 100 times we got exactly 1 baby go to their correct house. And 28 out of 100 times we got exactly 2 babies go to the correct house. Still, we see that 0 times do we have exactly 3. And only 3 out of 100 times were cases where all the babies went to their correct houses. So now I'm starting to get a sense that this is a very rare situation, that all 4 babies are randomly assigned to their correct households. Good. At the beginning, I thought it was like a 10% chance, but now I'm closer to a 3% chance. Now I'm thinking it's even more rare. Right? How confident am I in these results? Well, I'm more confident than I was when I only did it 10 times, but I'd still be more comfortable if it was bigger. How about if I jump to multiples of 100 and then I get to 1,000? Let's do this 1,000 times. A 1,000 times. After 1,000 times, we found that the most common thing that happened was 0 matches, right? We repeated this experiment 1,000 times, and it turns out that 398 of those 1,000 times were cases where none of the babies went to their correct households. 299 times, only 1 baby went to their correct house. 273 times, 2 out of the 4 babies went to their correct house. 0 times did we have exactly 3 babies. I'm starting to think that that's impossible then. right? Just based on this empirical probability. It's either incredibly rare, so rare we haven't detected it even once, or maybe it's impossible. And 4 out of the 4 babies going to the correct, all 4 babies going to the correct households, that's pretty rare. We only saw it 30 times out of 1,000. We're still thinking that's 3%. Okay, so I'm, again, even more confident that these results are fairly accurate, right? After 1,000 trials, that's pretty good. But you know what's better than 1,000 trials? 10,000 trials. Let's repeat it until we get to 10,000 trials. 3,000, 4, 5, 6, 7, 8. Right there. So the computer just did this 10,000 times. And out of 10,000 times, now these are the results we're getting. Now I'm starting to feel more comfortable that this is approaching the real answers, right? The theoretical answers. I'm still not 100% sure. I'm never going to be 100% sure based on an empirical probability, but the law of large numbers tells us that the more we repeat this, the more confident we are that these probabilities will approach the real ones. Okay, so if I had to give a probability based on these 10,000 trials, I would say that there is a 25.5% chance that exactly 2 out of the 4 babies go to their correct houses, right? Kind of like in this situation here. 2 babies were correct, 2 babies were incorrect. This scenario will happen approximately 25.5% of the time. Any questions about this simulation at all? No? No? No good? Okay, let's put this aside and let's find the actual answers using classical probability, right? So these are empirical probabilities, and they will approach the theoretical probability, which is the classical probability. So let's come over here and work on that. Now, if this was in COVID era, you'd be sitting in a classroom right now, and we would be doing this simulation using a deck of cards, is what I do. Instead of having a computer program simulated, what we can do is just have a deck of cards assigned to a group of students. And what we do is give one of each suit, so the club, the diamond, the heart, and the spade. Each one of those cards is assigned to a group, and they represent the mothers. And then we take a piece of paper like this, and you just randomly assign them to each corner, where each corner represents the different houses. So you have to write down each corner representing the different suits or the different colors based on like the simulation. But anyway, don't worry about that. What we want to do is write down numbers in a particular sequence where order matters. So what we want to say is that space number 1, right? Space number 1 here is baby number 1, and space number 2 is baby number 2, right? Household number 2. So when we have the case of, when we write down the case of when we write down the sequence 1, 2, 3, 4, I want this notation to indicate the case where all babies went to their correct space, and so this is all babies go to their correct houses. On the other hand, let's say we had this 2, 1, 3, 4. This is the case where baby number 2 went to house number 1, and baby number 1 went to house number 2. So these were both wrong, right? And this is the case where baby number 3 went to spot number 3, and baby number 4 went to spot number 4. So this indicates all 4 are correct. All 4 correct. Whereas this is indicating that this one is wrong, and these 2 are correct. So this is the case where 2 are correct and 2 are wrong. So if we adopt this notation, then if we want to think about all possible outcomes, everything that happens when this scenario is repeated, we can come up with a sample space. Good. So let's write down all possible outcomes by listing all possible ways of writing down the numbers 1, 2, 3, 4 when the order matters. So let's begin by thinking of all the ways in which we can begin with 1 and 2. Just kind of neatly organize them all. So all the ways in which 1 and 2 can happen, well, it's 1, 2, 3, or 4. Well, you know what, let me try and be a little neater with this. Okay, so I have 1, 2, 3, and 4. Okay. How about 1, 2, and then I can just flip around the 4 and the 3. And that's really all I can do, right? This is all the ways in which 1 and 2 can begin, and then all I have to do is kind of flip the last two. So now let's think of all the ways in which 1 and 3 could be at the beginning. I can put a 2 there and a 4 there. Or I can flip those around. 1 and 3 and 4 and 2. Good. And that's all the ways in which I can begin with 1 and 3. So how about if I begin with 1 and 4? 1, 4, 2, 3. Or 1, 4, 3, and 2. Okay, so I've covered every possible way in which 1 goes to its correct house, right? I covered 1, 2, 1, 3, and 1, 4. Of course, in this notation style, it wouldn't make sense to repeat a number, right? 1, 1, 2, 3 doesn't make any sense, right? Because baby number 1 cannot go to house 1 and also goes to house 2. It doesn't make sense in the context of this scenario. Good. Okay, so this is every possible way in which baby number 1 goes to house number 1. So let's explore every possible way in which baby number 2 goes to house number 1. So it could be 2, 1, 3, 4, or 2, 1, 4, 3, like that. Or 2, 3, 1, 4, or 2, 3, 4, 1. Good. Or 2, 4, 1, 3, or 2, 4, 3, 1. Good. So this is every possible way in which the number 2 goes to, baby number 2 goes to house number 1. Good. Now let's explore every possible way that baby number 3 goes to house number 1. Could be 3, 1, 2, 4, or it could be 3, 1, 4, 2, or it could be 3, 2, 1, oops, not 1, 3, 1, 4, or it could be 3, 2, 4, 1, good, or 3, 4, 1, 2, or 3, 4, 2, 1. Good. That's every possible way that baby number 1 can go to house number. Baby number 3 can go to house number 1. And finally, let's look at every possible way that baby number 4 ends up in house number 1. It could be 4, 1, 2, 3, or 4, 1, 3, 2, or 4, 2, 3, 1, or 4, 2, 1, 3. Or 4, 3, 1, 2, or 4, 3, 2, 1. Good. So I've covered every possible outcome, right? All possible outcomes. This is my sample space of my experiment, right? Capital S. This is my sample space. Well, there's 1, 2, 3, 4, 5, 6 ways that this can happen here. So 6, 1, 2, 3, 4, 5, 6. Okay, so they're all 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep. So there's 24. 24 outcomes. Good. Now let's go through and figure out how many matches were correct in each one. Right? So this is the case where there were 4 correct matches. Right? Because the baby number 1 went to house 1, baby number 2 went to house 2, baby number 3 went to house 3, and baby number 4 went to house 4. 4 correct matches. Here we have 2 correct matches. Baby number 1 and 2 went to their correct ones, but these were wrong. Here we have baby number 1 went to the correct house. Baby number 4 went to the correct house. These 2 are wrong. So this is the case where there were 2 correct matches. Okay, so correct, wrong, wrong, wrong. So this is 1 correct. This is correct, wrong, wrong, wrong. So this is 1. Correct, wrong, correct, wrong. So this is 2. Wrong, wrong, correct, correct. So this is 2. Wrong, 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 wrong. This is the case where there's 0 correct matches. So this is wrong, 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 correct. 1 correct match. Wrong, 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 wrong. This is the case where there's 0 correct matches. Wrong, 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 wrong. Again, 0 correct matches. Wrong, wrong, correct, wrong. This is 1 correct match. This is wrong, 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 correct. 1 correct match. Wrong, 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 wrong. So this is 0. Wrong, correct, wrong, correct. This is 2 correct matches. Wrong, correct, wrong, wrong. This is 1 match. Wrong, 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 wrong. 0 matches. Wrong, 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 wrong. Again, 0 matches. Wrong, 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 wrong. 0 matches. Wrong, wrong, correct, wrong. This is 1 match. Wrong, correct, correct, wrong. So this is 2 matches. Wrong, correct, wrong, wrong. So this is 1 match. And wrong, 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 wrong. 0 correct. And 0 correct. Good. Okay, so this is our sample space. This is all possible outcomes that can occur when this situation is considered. Good. So now that we went through and identified the number of correct matches, we can fill them out here. Number of times that 4 correct matches, exactly 4. Well, of all of them, there was only 1. It's right here. There's only 1 way that all 4 babies match, right? All 4 babies go to their correct mothers. There's only 1 way to do that. Okay, number of ways in which there was exactly 1 correct match. Okay, let's count them. 1, 2, 3, 4, 5, 6, 7, 8. So I got 8 times there was exactly 1 correct match. Number of times there were 0 matches. 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like 9 times there was 0 matches. 2 matches. There was 1, 2, 3, 4, 5, 6 times there was exactly 2 matches. And 3, yeah, it never happened. Let's think about that. Why would there be 0 times, right? This is now indicating that it cannot happen. It's impossible. Before, when we were looking at empirical probability, it kind of hinted that maybe it was impossible, but it always leaves open the possibility that it's just really, really rare and we hadn't seen it yet because we're just repeating the experiment over and over again. Who's to say that if I repeated the experiment 10 million times, eventually it happens once. Maybe it's a once in 10 million kind of situation. But this is classical probability. This is showing all possible outcomes, and none of them indicate exactly 3 matches. This means it cannot happen. So if we think about it, that should make sense, Because if we have exactly 3 correct matches out of the 4, right? You hand baby number 1, it goes to the right family. You hand baby number 2, it goes to the right family. You hand baby number 3, it goes to the correct family. There's only one baby left and one family left. It has to be the case that it matches, right? So if you have 3 correct matches and there's only one baby left, you're going to get the 4th one right as well, right? By default, it's the only baby left, the only family left, all the other ones were matched correctly, so the 4th one is also going to match, right? It's impossible to get 3 correct ones and then one of them is wrong. Good. Does that make sense? Any questions? No. Okay, so now that we have the exact number of ways that these events can occur, now we're ready to come up with probabilities. And remember that n of s is 24. So each one of these probabilities is going to be a fraction. The number of ways that it can happen, okay, so this is going to be 1 out of 24. 1 out of 24. Right? The number of the probability that we get 4 correct matches. Well, there's only one way that can happen out of a possible 24 different outcomes. Let's scoop this up here a little more. 3 correct matches. Well, we said that was 0. It can't happen. 0 out of 24. 2 correct matches. Well, that would be 6 out of 24. 1 correct match, that would be 8 out of 24. And 0 matches. 0 matches was 9 out of 24. Good. Okay, so now we can grab our calculator and convert each one of these into a decimal. And 4 out of 24 should be easy. That reduces down to 1/4, so we know that that's going to be 0.25. Okay. 8 out of 24 should also be easy. That's 1/3, right? That should be 0.33. So let's see, 8 divided by 24, right? And then 9 divided by 24. And then 1 divided by 24, and 6 divided by 24. So this guy we think is 0.00417, good, which is approximately 4.167%. Good. This one we're saying it's 0. Can't happen. 6 out of 24 is equal to 0.25, which turns into 25%. Eight out of 24 is equal to 1/3, which is equal to 0.33, which is approximately 33%. And 9 out of 24 becomes 0.375, which is equal to 37.5%. Good. So these are the classical probabilities. These are also called the theoretical probabilities. These are the actual probabilities, the exact answers. Good. And how do they match with our empirical probabilities? Let's see how they match up. So according to the empirical probability, when we were repeating this, we did this 10,000 times. We saw that 0 matches occurred 3,740 times. So we were getting about a 37.4% chance, and the actual answer was 37.5. So look, we were really close on that one, right? 1. Okay, so the empirical probability resulted in 0.328 when the answer was actually 0.333333. So again, really, really close, but not exact, but pretty close. And the probability that we got exactly 2 matches was 25%. Look, the empirical got 0.255. So again, very, very close. And the probability that we get all 4 correct should have been 4.167, and the empirical got 4.3, right? 4.32 if we went out one more decimal place after that. So again, really, really close, right? So what we should be getting out of this is reaffirmation that the empirical approach works as long as we do it enough times. If we hadn't done it enough times, let's reset the whole thing. And let's go back to just doing it, 10 times. Here is, well, actually, let's do it one more. Let's see the little animation thing one more time. See the animation thing happen one more time. There's the little stork guy. He goes, and there goes the babies. So we repeat the experiment once, and let's say we do it, 10 times. Okay, so I jumped a little. 1, 2, 3. There go the babies. Okay, so there, we did it 10 times. If I only do it 10 times, look how off my probabilities are. Based on 10 times, I'm thinking that the probability of getting 0 matches is 60%. Right? That's not correct. It should be 37.5, but that's because 10 trials isn't enough. Right? Empirical probability and the law of large numbers say that we need to do this a lot of times, many, many, many times, in order to feel confident that this probability will begin to approach the real one, right? And look, so far with just 10 trials, 4 out of 4 babies never came up, so I'm thinking maybe it doesn't happen based on this 10 trials. But the real answer is just 4.167. It's just a small probability, and it isn't detectable yet, right? But now if, again, jump to something big, like 1,000 times, you hit it, and it does it 1,000 times. See how that probability is beginning to look closer to the real answers? Right? Remember, this is supposed to be 25%, and I'm at 24.1. So I'm getting closer and closer and closer. Let's do it again. Wow, look at that. It's supposed to be 25, and now it's at 24.9. So it's really close. Right? If I want to get even closer, do it again. Do it again, do it again, do it again. Just keep going, 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 and eventually I will build confidence that these probabilities will approach the real answers. Okay, any questions? Any questions at all? Any questions at all? Any questions at all? One of the really tricky things about this problem is developing a notation style that helps you identify all possible outcomes, right? Adopting this notation style of just writing the numbers 1, 2, 3, 4, where the order matters, is important to be able to distinguish this situation. But in a different situation, you might have to readjust things. Maybe there's 5 babies. Maybe the order doesn't matter for some of them. So there's a variety of situations, right, that you can think of. Like, what if some of those babies are twins, and so there's like 2 babies? What are the odds that both babies go to the correct family? What are the odds that one baby is correct, one baby is incorrect, within the mix, right? Like, what if baby number 1 and baby number 2 are actually twins, and they're all babies. You can't tell them apart anyway, and you can't tell which one's which. What are the odds that both of those babies go to the same house and they're both correct? Okay, we're going to have to readjust our notation style a little bit in order to accommodate for that. So the notation style varies from problem to problem, and that's one of the many aspects that make statistics really hard. Right? Statistics is the study of word problems, and they can get tricky. Any questions at all? No? Move on? Okay, so that should wrap up all and everything I want to say about Chapter 5, Sections 1 and Section 2. So you guys should definitely be able to answer everything in 5.1 and 5.2. You should be wrapping that up soon, I hope. But we will move on to 5.3 now. So let me upload that part of it. Where would you be? Here? 5.3. All right, 5.3 and then 5.4 is where things begin to get tricky. So far I think they've been pretty easy. But in 5.3, things start to get a little bit more complicated. So make sure you pay really close attention to the definitions of these definitions found in this section, and make sure you stick to the letter of the definitions as you're working through these problems, because it's easy to make an assumption that shouldn't have been made, and then the whole thing just kind of unravels. Okay, so in 5.3, we're going to study independence and the multiplication rule. We're going to learn to identify independent events, right? So we're going to define it. We're going to think about what that means and how that affects our results that we're after. We're going to introduce a multiplication rule for independence events, and then we'll look at some examples. And we'll think about what it means to find at least, right? Compute at least probabilities, which is associated with multiplication rules. Okay, so the independence and multiplication rule. So two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F, right? Two events are dependent if the occurrence of event E in the probability experiment affects the probability of event F. Okay, so let that marinate for a little bit. We got one experiment. In that experiment, we have a bunch of outcomes, right? Simple events, the individual outcomes that are possible. We can group those up into compound events. And so now if we have event E and event F, that might be a simple event or it might be a compound event of their own, then we identify them as being independent if the occurrence of one of those events is independent. It does not affect the probability of the other event. Okay, so let's look at some examples. Otherwise they are dependent. If the two events affect each other, the occurrence of one event does affect the probability of the other, then they are dependent. So here's some examples. Suppose you draw a card from its 52 card deck, and then you roll a dice. Consider the two events. Draw a heart and roll an even number. Okay, so think about what that means. You're in Las Vegas and you decide to play one game where you just pull a card. You're just betting on what that card is. And maybe you bet some money down that it's going to be a heart. One card is drawn. Is it a heart? I go on the table on the other side and go, okay, I'm just going to roll the dice here. And I'm just betting that when I roll a single die, it's going to be an even number. Okay? Can you see that these two events have nothing to do with each other? They're completely different, right? They're completely different situations. If it turns out that you're about to pull out your card and draw out a heart, and you're thinking to yourself, what is that probability? What is the probability that we draw a heart? Let's think about that for a second. Probability that one card is selected and that card is a heart. Okay, so how many cards are there? There's 52 cards. And of those 52 cards, 13 of them are hearts. So it's 13 out of 52. Good. Which reduces to 1/4, which reduces to 25%, 0.25. Come on, Peter. 25, which turns into 25%. Good. Okay. Now, the probability that we roll an even number is the probability that we roll one single die, and the answer is even. Well, I'm assuming it's I think it says it. Does it say six-sided die? Well, I'm assuming it's a six-sided die. That's a standard type of die. And so there's 6 possible outcomes. And how many of those outcomes are even? Or it could be the 2 or the 4 or the 6. There are 3 possibilities, which turns into 1/2 or 0.50 or 50% chance. Good. And remember, this 3, don't confuse this as we roll a 3. That's not what this is saying. This 3 is identifying the possibility that it could be a 2 or a 4 or a 6. Right? Our die could have a result of a 2, 4, 6. And this 6 comes from the fact that we are assuming it's a 6-sided die. There are 6 possible outcomes. Okay? But if I'm sitting at the table about to roll my die, and I'm like, oh, come on, even. I'm going to make some money. Even, even, even. And my friend comes and he says, oh, by the way, I played this other game, and it turns out it was a heart. Does that have anything to do with me rolling an even? Nothing. Right? Just useless random information. You got a heart? Great, good for you. I'm trying to roll my dice over here. Right? It has nothing to do with it. They're independent events. The probability that my friend gets a heart in that other game has nothing to do with the probability that I roll an even in my game. Or the other way around. Right? If I rolled it and I got an even, I run over there and go, guess what? I got an even. Doesn't affect his game. Right? He's playing a different game. It has nothing to do with each other. Okay? So these two events are independent. They have nothing to do with each other. Okay? All right, another case. Suppose a 40-year-old woman who lives in the United States is randomly selected. Consider the events woman number 1. Suppose 2 40-year-old women who live in the United States are randomly selected. Consider the events woman number 1 survives a year, and the other event of woman number 2 survives a year. Okay. Really important to emphasize that these are randomly selected women, so they likely have nothing to do with each other. Like, they don't know each other, they don't live in the same city, they don't work in the same office building, they don't go to the same school, they don't shop the same stores, they don't have the same bank account, they don't go to the same bank, they have nothing to do with each other. So the probability that one woman survives a year has nothing to do with the other one. Or the other way around, the probability that one woman dies does not affect the other woman. Right? Because they don't know each other. There's nothing to connect them. Right? If during the middle of the year, we let this person know, hey, by the way, it turns out the woman number 1 died, it doesn't affect this person's chance of surviving the year at all. Right? It doesn't matter. They're unconnected. Right? So these have to be independent as well. Good. Questions? Is it clear? And that's really, really reliant on the fact that they are randomly selected, and by that we assume that they have nothing to do with each other. They don't know each other at all. Okay, so the probability of one living for the next 12 months has nothing to do with the other person also surviving the next 12 months. Or the other way around, one of them dying doesn't affect the other one. The odds that the other person dies also are not affected. On the other hand, what if these 2 40-year-old women live in the same apartment complex? The event that woman 1 survives a year and woman 2 survives a year are now dependent. Why are they dependent? Because now they have something in common. They live in the same apartment complex. So they're no longer complete strangers to each other. There is a connection going on there. So if one woman dies, it might affect the chances that the other person dies. Right? Think about why that is. What if, halfway through the year, we pick these 2 women, they live in the same apartment complex, kind of visualize them, and I tell you woman number one died, what are the odds that woman number two also died? Well, how did woman number one die? Right? What if she died in an apartment building fire? Right? The building caught on fire and woman number one died. Well, that definitely affects the chances that woman number two also died. Okay. Okay, well, forget that. Okay, what if woman number one died because there was a shooting in front of her house and she was, just about walking out the door and she, got hit. Okay, there was a shooting in front of the building and that's how she died. Well, maybe woman number two was there too. Who knows? Maybe she also died. It affects her. Okay. And not just in a negative way, but in a positive way. The fact that she survives the year, everything was wonderful. She survived the year. It means that her building didn't catch on fire. There was no shootings in front of the building. There was no problems. So therefore, that increases the chances that woman number two also survived the year. Right? If this woman had no problems living there, then this woman likely also had no problems living there. Not guaranteed, but it's just more likely. Good. It could also be connected to the apartment building in a sort of roundabout way. Maybe the reason this person died that year is because there was contaminated fruit in the local farmer's market. She went out to the local farmer's market, bought some fruit. It turns out it was contaminated, and then she died. Okay, well, if this person and this person live in the same apartment building, there is a chance that this woman also went to the same farmer's market. And there's a chance this person also ate the same contaminated fruit. So if this person dies, it also is connected to this person. Right? Again, all associated to the fact that they live in the same apartment building. Good. Good. Questions? So, this kind of stuff is really relevant to insurance companies that are always interested in knowing what are the chances that something bad will happen, and therefore they'll have to pay. So what are the odds that somebody dies, if they have life insurance, or if they're considering opening a policy for somebody. And so they take things into consideration. Now, they're not allowed to take some things into consideration by law. They can't ask about health conditions, for example. But in most cases, I think there are a few things that they can consider, like organ transplants, for example. If you had an organ transplant, I think you have to declare it. But they can ask you things like, do you smoke? Have you ever smoked tobacco? Alcohol. How much alcohol do you consume? Have you ever had any traffic violations? Right? So they're looking for things that are associated with expensive events for them, right? People that die young and therefore they have to pay a big payout for life insurance have certain things in common, right? Drinking could be an indicator. The kind of car they drive could be an indicator. All kinds of things. Where they went to college could be an indicator. What their major was in college could be an indicator, right? All kinds of stuff can be pumped into a computer model that helps them try and come up with a likelihood that they're going to have to pay out on a life insurance situation. Good. Are there any questions about these then? Why these two are independent and this one is dependent? So in your homework, there will be some questions where you're asked to identify whether something's dependent or independent. And in some cases, it is painfully obvious that they are independent, such as case A here, pulling a card from a 52 deck card and rolling a die. I think that's super obvious that they're independent. I might ask you, what is the probability that I get struck by lightning? And consider that, and the probability that I win the lottery. Winning the lottery and being struck by lightning have nothing to do with each other, right? The likelihood of one does not affect the likelihood of the other. Right? So those two events are definitely independent, right? What is the probability that I get in a car accident this year and what is the probability that it will rain it will rain on New Year's 2030, right? Me getting in a car accident this year and the fact that it rains in Los Angeles on New Year's in the year 2030, those two things have nothing to do with each other, right? Now, if I had said rains tomorrow and also what's the probability that I'm in a car accident tomorrow, well, okay, raining, car accident, they might be connected somehow. So those would not be independent, right? But rains 10 years from now and me getting in an accident this year, those two are definitely independent of each other. Good. So sometimes the word problems are really obvious that they're independent of each other, and sometimes they're not. And if they're not, then we need a very specific mathematical definition for us to rely on to be able to tell if something is dependent or independent. And our definition is this. Two events E and F are independent if the occurrence of event E in the probability experiment does not affect the probability of event F. Okay, so we find the probability of them. So we find the probability of E, and then we throw into consideration the fact that event F occurred, and then we recalculate the probability of E, and if that additional information had no impact, then we know that the two events are independent. If it did have an impact, if something did change, then they would be dependent. Okay, and so we'll get into examples like that. Okay, so the multiplication rule for independent events. So step one is going to be to determine whether event E and event F are independent, and that in and of its own, it can be very tricky. But assuming that we know that event E and event F are independent, then the multiplication rule tells us that the probability of event E and F is equal to the probability of E times the probability of event F. Got it? Got it. For example, let's look at an example down here. The probability that a randomly selected female aged 60 years or older survives a year is 99.186, according to the National Vital Statistics Report. What is the probability that two randomly selected 60-year-old females will survive the year? Okay, randomly selected. We said that two randomly selected 60-year-old females are independent. So, probability that woman number one survives is equal to 0.99186. Probability that woman number two survives the year is also equal to 0.99186. And these two events are independent, so the probability that woman number one survives and at the same time woman number two survives is equal to the probability that woman number one survives times the probability that woman number two survives. Okay, that's what we want to know. What is the probability that the two randomly selected 60-year-old women will survive the year? Right? And that's because they're independent. This is because these are independent events. So all we have to do is multiply them. Now the probability that woman number one survives was 0.99186. And the probability that woman number two survives is 0.99186. Okay, so we just have to multiply these two. And so that it matches intuition, remember that I'll remind you like a little property of numbers. Here is the number line. Here is 0, here is 1, here is 2, and so on and so forth. Okay, the numbers. if I pick a number over here that's strictly bigger than 1, if I pick two numbers that are over here, any two numbers, A and B, any two numbers, and I multiply them, the result of their multiplication is going to be even bigger, right? If I pick a 1.5 times a 3.7 and I multiply them, I'm going to get an even bigger number, right? That's always true for these ones. On the other hand, if I pick numbers that are between 0 and 1, somewhere in here, right, not including the 1, not including the 0, just any two numbers in here, say I pick this one here and that one there, any two of these numbers and I multiply them, their answer is going to be even smaller. Good. Even smaller than either of the two. Does that make sense? So bigger than 1, two numbers are selected, and I multiply them, the answers are going to be even larger. Larger. Like 2 times 3, the answer is 6, right? It's bigger than those. Or 3.7 times 4.8, the answer is going to be even bigger than those, right? So multiplication leads to bigger numbers as long as the selected values are both bigger than 1. But with decimals, when we're looking at decimals, something weird, not weird, but it just, something different happens. Whenever we pick two decimal numbers, right, below 1, not including the 1, and we multiply them, then the answer to the multiplication is going to be smaller than either of those. So the more decimals we multiply between 0 and 1, the smaller it's going to get. Good, good, good. Okay, so we multiply these two, and I know that the answer is going to be smaller, a little bit smaller than 99,186. Good. Questions, 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 questions? So 0.99186 to the power of 2, squaring it, I get that, and C gets a little smaller, 0.9838. 9838. Right, so approximately 98.38% chance. The probability that one individual woman survives a year is a 99.186% chance that one randomly selected woman is selected that she will survive the year. But now if we're looking at two women, the probability that both will survive the year, now we're down to 98.38. Any questions? No? Okay, 98.38, that's what I did there. Okay, now consider this example. A manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year. After it is purchased, right? So that's kind of sad. They know that, people that watch infomercials at 2 in the morning and want to get fit are going to order this really expensive piece of equipment. And they know that 30% of them are just going to receive it, sign, thanks for dropping it off, and they'll stick it in the garage and they won't even touch it. It'll stay in its box for at least a year. Maybe sometime after that, some of them will eventually open it and try it out. And maybe some of them are just never ever even going to open the box. It's just going to sit there for years and years, and then they'll donate it to somebody. So they know a good chunk of the people don't actually use the equipment. They also know that 10% of all their machines are defective, right? They will break. They won't work properly. Okay. If there is a 1-year warranty on the equipment, what proportion of customers will actually make a valid warranty claim? In order for it to be a valid warranty claim, both things have to happen. You have to be a customer that receives a faulty device, and you have to be one of the customers that actually tries it out in the first year so that you can have a valid claim. if you wait longer than a year to try it out, if you're one of these 30% of people that don't use the equipment in the first year, then even if you realize that you have a defective product, once the year is up, then you're out of luck. You can't take it back anymore, and you can't get your money back. You can't get it fixed. You're stuck with it. Okay? Now, the forces in the universe that make this device faulty, and the forces in the universe that makes this person be lazy and doesn't actually try the equipment, are those dependent in any way? Are they associated in any way? No? Is it clear that they're not associated in any way? Right? Whatever it is that's defective. What's the defective about it? I don't know. Maybe 10% of the machines, the bolts just kind of snap in two. They're made out of a weak metal, and when you start doing exercise on them, the bolt just snaps, and then the whole thing breaks. Okay, maybe that's what it is. The forces in nature that made, not just in nature, but in the universe, that made that bolt weak. Maybe the machine that made them was defective, or maybe the raw materials that they used were contaminated, or maybe the guy that was running the machine that did those didn't know what he was doing. Who knows, right? But whatever makes the machine defective has nothing to do with the customer who orders the machine, receives the machine, and then decides not to even open the box, right? Those two things are independent. Good? Okay, so in order to have a valid claim, it's the probability that we have a valid claim, then we need two things. We need the person to have a defective product, and it has to be somebody that uses the equipment within the first year, so that can identify that they have a defective product. This is the machine within 1 year. Within 1 year, right? Those two things have to happen. And as we said, those two things are independent. Defective times the probability the person uses the machine within 1 year. Good. So 10% defective, 10% of all machines are defective. Good. And we said that 30% of their customers will actually use the equipment within the first year. So this is 30%. So 10% of 30%, we multiply those two things together, and we're going to get 0.03, which is 3%. Got it? So this is the expected value, 3%. How do we interpret this? So even though 10%, right? So although 10% of products are defective, only 3% will be returned, will be refunded or returned. Good? Questions? So, one great idea to become rich, ready? Come up with a silly product that's totally bogus, doesn't work, but offer a 100% money back return. Great. But then put a few conditions on it. So maybe in order to return your product, they have to write a letter, handwrite a letter, and mail it snail mail style, mail it with a request for a refund, right? So, let's say I decide to offer this pen. Look at this pen. It will never, ever run out of ink, ever, forever and ever. And it will never break, and it's indestructible. Look, you can run a car over it. It's beautiful, and it's indestructible. And let's say I know that it's total BS and it doesn't really work, right? I mean, even 100% of them are faulty. But I'm only charging $20 for this pen. Good. So let's say I know 100% of them are faulty. So I'm making up a new problem here, just to kind of get an example. So let's say I know 100% of my pens are defective. But I also know that many people will receive it and they won't even really check it, right? People order stuff on these 3 a.m. infomercial things and they just receive it and they might not even check it. So let's say I know that only, it's a pen. Let's say 70% will check the pen. Will inspect the pen. It seems reasonable. Okay, in order to return it though, I offer a 100% money back guarantee. In order to receive your money though, first of all, you have to call us, and there will be, I'm guaranteeing, there will be a 1 hour wait. All right, so must call. And let's say I know that when people call, I've been checking, a lot of people just give up. They're not going to sit there for a whole hour waiting, right? So a lot of people give up. Let's say only 20% of the people, 20% of the people will wait on the phone, for an hour to talk to a customer service person. Okay, once they finally get through to somebody, that person is going to say, okay, I understand. We need you to write us a letter and tell us in written form that you want a refund. And that's already a big obstacle, right? So, and I'm just guessing these numbers. Let's say I decide that, based on intuition and a little bit of research, only 1/4 of the people that are told that they have to write a letter and mail it in to get a refund, only 1/4 of them actually do it. So 25% will write the letter, will write a written request, a letter to request the refund. A refund. Okay, fantastic. That's the process. First, you order the pen. It's defective. It's a broken piece of garbage pen. Only 70% of the people will inspect the pen. Only 20% of the people will actually wait for an hour before they get to somebody. Only 25% of those people will actually send in the letter requesting for a refund. Once the company receives the letter to request for a refund, they will send them a little bag with like a self-stamp thing. What do you call it? Like a little box or something to return the pen. So how many people are actually going to go follow through the process of putting the pen into the little return envelope thing and go over to the mailbox and drop it in? Let's say we've discovered that 35% of the people follow through and will return the pen. Return the pen in the self-addressed envelope thing we mail them. Does that make sense? So in order to be able to get a refund, what's the probability that you get a refund? Okay, probability that you get a refund. Okay, well, a bunch of things need to happen. First of all, you got to get a defective pen. Okay, well, that will happen, right? They're all defective. And you have to be one of the people that inspects it, and you inspect it. And you have to be one of the people that will call and wait. and you have to be one of the people that writes a letter and sends it and says, hey, please give me my money back. This pen was junk. And you have to be one of the people that when you receive that envelope, like please return it, here's a self-addressed envelope, go drop it off at the mailbox, you have to be one of the people that actually follows through and gets it done, so we'll return it, right? If all those steps are followed, then you get a refund, okay? So these are all, assuming these are all independent events, right? The fact that the pen is defective has nothing to do with whether you're someone that's actually going to inspect the pen. And whether you inspect the pen or not has nothing to do with whether you're someone that's willing to sit in the phone for an hour till somebody answers it. And it has nothing to do with whether you're someone that will actually write a letter, print it out, put it in an envelope, put a stamp on it, mail it to wherever they tell you to mail it to. Just a simple letter that says, please refund me my money. This pen didn't work, didn't live up to the expectations. I want my full refund. Please send my return envelope to a certain address. Okay, and then you get that return envelope and then you actually return it. You got to put it in there and you got to go over to the mailbox or the post office and return it. Okay, so all those things have to happen. They're all independent. So this is equal to the probability that you get a defective times the probability, times the probability that you inspected, times the probability that you call and wait, times the probability that you actually write a letter, times the probability that you return it. Oops. Come on. Okay, so maybe the people can start to think about whether or not we're just assuming that they're all independent events here for the purposes of this. Somebody could fight me on whether they're actually independent or not. Maybe someone that is willing to wait an hour for a phone call might be more likely to write a letter. But just for the purposes of this, let's just assume that these are all independent events. So the probability that you get a defective one, we said that was 100%, right? They're all defective. They're all silly pens. The probability that you inspect it, you're one of the people that inspects it, is 0.70. The probability that you're someone that's going to wait for a whole hour till you get a hold of someone on customer service, that's 20%. Probability that you will be someone that writes a letter is, say, 25%. And probability that you're someone that follows through and returns it once you receive the envelope is 0.35. So let's multiply those guys together. So we have 1 times 0.7 times 0.2 times 0.25 times 0.35. Look at that. That turns into 0.01225. 0.1225. That is 0.01225. That turns into 1.225%. That's really small, right? So even though you're selling really crappy, defective pens, all of them, don't live up to the promises. It's just a bunch of junk. If you set up this whole process to return and you 100% return money back guarantee, you do give back the money as long as all these things are satisfied, it's expected that only 1.25% of your sales will be returned. That means you get to keep the rest of it. 98% of your sales you'll just keep, even though you're selling a bunch of crap, right? There you go, $1 million idea. Sell junk to idiots that buy crap in the middle of the night and infomercials. Or, I guess now spam, right? You get hit with a bunch of spam to buy junk. So there you go. I want a commission if anybody does anything like this. Or if you get busted by the FBI for doing an illegal thing, then don't blame me. I'm just doing a theoretical example here. Questions, 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 questions? Well, let's go a little bit further on this. Let's say that I'm selling them for 20 bucks each. $20 for each pen. And let's say that I have a very successful year, and in that year, I sold 125,000 of these pens. Sold. Okay, so if we multiply 20 times 125,000, that's going to be 250 with 1, 2, 3 zeros, 1 extra 0. That's going to be $2,500,000 in sales. Good. 2.5 million by selling $20 pens, and I sold 125,000 of those pens. Now, again, they're all junk, so I'm expecting that there will be a refund process, but I'm expecting that only only 1.225% returned. Good. So if we multiply those two, let's go back to our calculator. So this decimal, now one shortcut, by the way, of your calculator is this little ants button right above this negative sign. So if you hit second and then that little ants button, ants, it's referring to the very last result. So you don't actually have to type in the 0.01225. You hit ants, it means that previous decimal. And now I want to multiply that by 250. Oh no, 2,500,000. So there's 500,000. 1, 2, 3. That means I'm going to have to return $30,625. That means I get to keep the rest. 2,500,000. 1, 2, 3 minus the previous answer. That means I get to keep $2,469,375. Not bad for selling a bunch of junk pens, right? Of course, that's not profit yet. I still have to pay for several things. Well, for one thing, even though they're a bunch of junk pens, they cost me something, right? So maybe I bought them for like a nickel each, some sort of junk thing. So then I have some expense there. And then, of course, I'm going to have to pay for shipping the junk pens out initially, and then some of them that get returned, I have to pay for them to return them to me, and then I have to pay for someone to help me with the processing of the sales and processing of the returns. So I have a bit of overhead to pay here, but I bet a lot of that money is still profit. So you can still turn this into a multi-million-dollar profitable business selling faulty pens. So what do you guys think? We in business together? I want like a 10% commission for the idea.
Yeah.
Okay. Any questions on all this? Okay, so the moral of the story here, the point of all this, is that if they are independent events, right? I'm assuming that it sort of makes sense that they would be independent. Someone could argue that maybe some of these things are not independent, but let's just assuming that they're all independent for the purposes of this section. Assume all independent events. Then we multiply them together. The probabilities that all of them happen at the same time, since they're all independent, is equal to finding each one of those probabilities separately and multiplying them together. Right? The probability that I get married this year, win the lottery, get struck by lightning, and that my friend Bob becomes governor of California. Like, all of those things are independent from each other. The probability that they all happen this year, well, we just find their probabilities separately, multiply them all together, and that's the odds that all of them happen. Good. So if you want to know what is the probability that you win the lottery, you get struck by lightning, and you die on a plane accident all this year, well, find them separately. They're all independent from each other. Find them separately, multiply them together, and those are the chances that that will happen. Any questions, any questions, any questions? Okay, this is just the author doing the same thing back to the manufacturer of equipment. So 10% are defective, 30% know that they will be defective because they use it. So the probability that they're defective and they used it is equal to the multiplication of the two. So we get to 3%. Good. That can extend out, like in my example, there's a lot of them. So that can extend out to several. The probability that event E sub 1 and E sub 2 and E sub 3 and E sub 4, the probability that they all happen at the same time, if they're all independent, comes to this. Just find them separately and multiply them together. Okay, so back to the women. The probability that a randomly selected female aged 60 years or older will survive the year is 99.186% chance. What is the probability that 4 randomly selected 60-year-old women will survive the year? Now we got 4 of them. Okay, what is the probability that woman number 1? You know what? Instead of doing number 1, I'm just going to do sub 1, if that's okay. Woman sub 1. This is the first woman. What's the probability that she survives? Well, actually, that's still ugly notation. Let's say probability that woman number 1 survives. Well, that's just 99, 0.99186, and that's the same thing as the probability that woman sub 2 survives. That's 0.99186, right? For any independently chosen woman, that's 40 years or age 60 years old. The odds that they survive the next 12 months, are 0.99186. 4 survives 0.99186. Okay, but now if one's probability that all 4 survive, that's going to happen if woman 1 survives, and at the same time woman number 2 survives, and at the same time woman number 3 survives, and at the same time woman number 4 survives. Right? All of these things have to happen. We're assuming they're all independent because they're randomly selected. All 4 independent. Right? Again, to this randomly selected, it's important that they're randomly selected. They have nothing to do with each other. They may not live in the same city. They didn't go to the same school. They don't shop the same store. They don't have the same doctors. They don't use the same medication. They have nothing to do with each other. So if one of them dies, it does not impact the probability that the other one dies. Okay? Or if one of them lives 12 months, it does not impact that the other person. Right? If they have something in common, maybe they're related to each other, well, if one of them dies, it might affect the probability that the other one dies. Right? What if, one of them dies of a heart attack? Well, if the other one has been, a sister that's been living with her whole life, they likely eat the same things, they have the same lifestyle, the same routines. It impacts it. It doesn't guarantee or anything, but it has an effect on the likelihood that the other one would also die. Good. But they're independent. They're all randomly selected. So that means that we get to break this up into the multiplication of 4 separate probabilities. Woman number 2 will survive times the probability that woman number 3 will survive times the probability that woman number 4 will survive. Okay. Now each one of these happens to be the exact same probability, 99186, times 0.99186 times 0.99186 times 0.99186, right? And I'm going to wrap it around parentheses because there's so many, the decimal and then the multiplication indicator kind of get confusing. So I could do that. And there's 4 of them being multiplied. They're all identical. So another thing we could do is write it using exponents this way. This is equal to this raised to the power of 4. And now we can come over to our calculator and figure out what that is. And remember that with decimals between 0 and 1, that the more we multiply them, the smaller things get. So I'm expecting that my answer will be smaller than this one. Right? With numbers bigger than 1, the more we multiply, the bigger the number gets. But with decimals, the more we multiply them, the smaller the final output would be. So I can do this, and then I'm going to use this little caret symbol here, and that indicates that it's being raised to a power of, I'm going to say 4. So this means a multiplication of this decimal times itself 4 times, and I get that. A little bit smaller. So now it's only 9678. Right, so now we're at a 96.78% chance that all of them will survive. The probability that exactly one of them will survive is 99.186%, but the probability that all 4 of them will survive is 96.78. So it's starting to slowly creep lower, right? Any questions? Questions? No? Yep. No? Okay, so then the author did the same thing. All 4 survive is equal to the first one survives, the second one survives, the third one survives, the fourth one survives. Notice the notation is a little bit different. Again, statistics, it's hard. One of the things that makes it really hard is the notation. Okay, the next example. The probability that a randomly selected female aged 60 years old survives is 99.186% chance. What is the probability that at least one of 500 randomly selected 60-year-old females will die during the course of the year? Okay, so we need to think about the complement of this. The complement of at least one dies is that none die, right? The complement of at least one dies is none die, right? So let's think of, for example, like a table of all possible outcomes. I have 500 women, 500, right? There we go, yeah, 500. So 500 women are observed for a whole year. What are the kinds of things that can happen? After one entire year, maybe 0 of them die. Like that's one possibility. 0 die after one whole year from the 500, right? After one whole year, maybe a whole new group of 500 women. After one whole year, exactly one of them died. Yeah, one died of the 500, right? Or maybe a whole new group of 500 women. Maybe after an entire year, maybe 2 of them die, right? Or maybe 3 of them die, and so on and so forth. And of course, I could have the extremes over here as well. 499 of them died, or all 500 died, right? This is all possible outcomes that can happen. Good. Associated to all of these individual exact cases are probabilities. What's the probability that exactly 2 die of the 500? What's the probability that exactly 3 of the 500 die? Right, so we can find all these individual probabilities. Probability that 1 dies. What's the probability that 0 die? Okay, now the statement, at least 1 dies, that encompasses all of these cases over here. Good. So one way to approach this is to find the following. When we say the probability that at least 1 of the 500 dies Well, this can happen in several ways. Maybe exactly, oops, exactly one dies, right? Or maybe exactly two die, or exactly three die, right? All of these statements satisfy at least one died, right? Dot, 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 at least one died. And it goes all the way out to the extremes. Maybe exactly 499 die, or exactly all 500 die, right? All of these conditions, all these situations, all these outcomes, 2 died, 1 died, 3 died, 409 died, 500 died, all of these satisfy the statement at least one of the 500 died. Good, good. We know from our work from prior sections that these things are disjoint events, right? If or 3 died. I can't have both happen at the same time, right? So these are disjoint events, right? Let's put those in there. These are all disjoint events. I should put all these disjoint events. Okay, so we know that that means that this probability must be the summation of all these. The probability that exactly 1 died plus the probability that exactly 2 die plus the probability that exactly 3 die plus dot 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 all the way out to the probability that exactly all 500 die. Good. So the answer I'm looking for is going to be to sum up all of these probabilities here to here, right? All of these probabilities, I want to sum them all up. Sum them all up. And that's going to be my answer to the statement, at least 1 dies. Good. Any questions about that? And each one of these might be really hard to find. And there's a lot of them. So that's definitely not something I'm looking forward to doing, right? Some of these might not, a couple of these might not be too hard to find. The extremes, like what's the probability that all 500 die? That one's not too bad. But the probabilities anywhere in the middle, what's the probability that 86 die? What's the probability that 123 die? Ugh, there's a lot of them and they're really complicated. So I don't want to do it this way. So we want to take advantage of complements. I know that if this is a proper probability distribution, I must know that the sum of all of these, all of them, must add up to 1, right? Let me make a little space right here. Like, I'm going to write something on there. There, just wanted to make some space here. So I know that this is a proper probability distribution. It accounts for all possible outcomes when 500 women are observed for a year. Either 0 die or 1 die or 2 die or 3 die, dot, 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 all the way up to 500. These probabilities, which I don't know, but I know they exist, there must be some probability for each one of these possible outcomes. I know that the sum of all of these must add up to 1, right? 100%. And I know that from here to here is the answer I'm looking for. So what I can do is note that if I just find the answer to this one, then 1 minus this one should give you the sum of all of these. Good. And so at least 1, well, I should put it on this side actually. At least one is all of these, And its complement is this one, none. None and at least one are complements of each other. Right? Together they partition all possible outcomes. Good, 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 good. And this one's much easier to find. So what we're leading to is that even though this is technically a correct way of doing it, you definitely don't want to do it this way, right? That's just leading down an ugly, ugly rabbit hole here. So what we want to do instead is say that the probability that at least one dies is equal to 1 minus the probability that none die. All 500 survive. All 500 survive. Good. Which is equivalent to 1 minus, okay, let's start the process here. Woman 1 survives. And at the same time, woman 2 survives. Right? I want all 500 to survive. Survives. And dot, 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 get to the very end there. The very last one is, and woman number 500 also survives. Right? That's what we're after. That's all 500 survive. Well, that's going to be 1 minus the multiplication of each of these individually, right? Since they're all independent. All independent. They were all randomly selected. Right? All 500 are independently selected women. So I get to find the probabilities of each one of these survive and multiply them together. Probability that woman 2 survives times dot, 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 dot. And then the last one is the probability that woman number 500 survived. Good. Luckily, they're all the same decimal. So this is going to be 1 minus 0.99186 to the power of 500. Right? We multiply this by itself 500 times. That'll give us our decimal. And then 1 minus that is the probability that at least one of the 500 women will die. Okay, so let's put that into our calculator. And we get 1 minus, and I'm going to put this in parentheses just to make sure it doesn't mess with it, 0.99186 to the power of 500. Close parentheses. Okay, something like that. Enter, and that's what I get. 0.9832. 9832. Let's go over here. 0.9832 or 98.32% chance. There is a 98.32% chance that at least one of the 500 women will die. 500 women will die. Any questions about this whole process? No. Okay, so there's what the author did. Pretty much the same thing. Probability that at least one dies is equal to 1 minus the probability that none die, which is the same thing as saying all will survive. And therefore, it's going to be 0.99186 to the power of 500. This is the probability that all survive. Punch it in your calculator and you get that. So there's a really, really high chance, 98.3% chance, 32% chance, that at least one or more of the 500 women will die in the next year. Good. Good, good, good. Okay, quick little summary of the probability rules we have so far. We know that probabilities of any event must be a value between 0 and 1 inclusive, right? So if E denotes any event, each probability must land between 0 and 1 inclusive of the endpoints. The 0 means that it never happens. A 1 means that there's a 100% chance it will happen. It will definitely happen. We also know that when we come up with our sample space, each individual possible outcome, simple outcomes, simple events, can be denoted with lowercase e sub 1, sub 2, sub 3. So this means that there are lowercase n number of outcomes in this sample space. And we know that the sum of the probabilities of the simple outcomes must add up to 1. We also know the addition rule if two events are disjoint. If E and F are disjoint, then the probability of E or F is equal to the probability of E plus the probability of F. If E and F are not disjoint events, then there's a more general rule. The probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. We know the complement rule, that if E represents any event, E to the power of C, this little thing here, represents the complement. And we know that the probability of E plus the probability of E complement must be equal to 1, and then from there we can get something like this. And then today's rules about multiplication, we know that if events E and F are independent events, then the probability of E and F is equal to the probability of E times the probability of F. Okay, so next we're going to get into conditional probabilities, and that's when things really get confusing. So make sure that you're really well caught up to where we are so far, because if you're not caught up, then when I start talking about 5.4 stuff, it's really going to confuse you. Okay, so make sure you read the book, you watch these videos, and you do the homework so that you can be prepared to tackle the concepts from 5.4 conditional probability. Okay, this is a good place to stop for today. Are there any questions on anything? Questions? All right, then. I will see you Thursday. Cool. All right, tackle that homework.